Good morning, one and all. Welcome to the next class of data communication networks. In our previous class, we started discussing about our unit number 3, which is network layer. So, network layer, which is the third layer of OSI model, performs different types of functions. First and most important function is it receives data from the transport layer, which is in form of segments, and converts it into datagrams. The network layer is responsible for one of the very important functions called host-to-host delivery. It ensures that the datagram that has been generated has to be transmitted from the source to the end destination. To implement this host-to-host delivery, the network layer performs two important functions called forwarding and routing. So we try to understand what do you mean by a forwarding function and how it was different from routing function. So to implement the host-to-host delivery, the network layer tries to connect different intermediate nodes called as routers. So the datagram generated by the source before it needs to reach the destination will be traveling through multiple intermediate nodes called routers. So here in a router, the datagram has to enter through an input port and it has to leave from one of the output ports. So from which input port it enters and from which output port that particular datagram leaves will be referred by a process known as forwarding. Now at the same time, between the source and destinations we may have multiple routers involved. But for transmitting of data, we will be using only certain set of routers. So the path which a datagram travels from the source to destination is called as route. And the process of determining the route is referred as routing. So forwarding is within the router, but routing is connecting different routers so that a datagram reaches from source to the destination. Now coming to the different types of services provided by network layer, where we can have services with guarantee, services not only with guarantee but minimum delay expected, then bandwidth assurance we can be provided so that there will be no packet loss. Then the jitter between the two packets transmitted by the sender should be same with the jitter generated at the receiver between the two packets that are received. So all those are called as various services which can be provided. And we have the first type called internet, which is the best effort delivery, will not guarantee any of the above parameters. It just tries to ensure or provide the path to transmit from source to destination. When you are expecting all the services which we mentioned earlier with a reliable guarantee and delivery of packets in the order, we will be going with another kind of circuit called asynchronous transfer mode. Then next, based on the type of service provided by network layer, we have two types of networks called as virtual circuit networks and datagram networks. In our previous class, we discussed about what do we mean by virtual circuit network, how it is implemented, then what are the elements involved, then what is the process of implementation of virtual circuit network, then we try to discuss what are the different signaling messages and signaling protocols, and the second part, which is the datagram networks, is the thing which we are going to discuss in today's class. But before I discuss datagram, let me make you quickly understand. Virtual circuit network is a type of network service in which before a datagram is transmitted from source to destination, a path has to be established between the source to the destination along with the routers which are involved should be made a part of it. A virtual path has to be created and all the packets will be traveling through that virtual path. So we need to make a reservation of the resources, and in between source and destination we are using routers. For the routers we have to provide the forwarding tables so that they will be able to forward the datagrams. The only difference between virtual circuit networks from other kind of networks is instead of using a destination address for transmitting the data. Here we will be using virtual circuit identifier, which will be changing from link to link. Okay, so based on the different links which we are using, the virtual circuit identifier varies. And one more important thing that we need to remember about network layer is network layer. For implementation of host to host delivery, we are using a special type of address called internet protocol address, in short IP address. The current version of IP is IPv4, and the future version which we are planning for migration is IPv6, that we will be discussing in the coming classes. Okay, so this is a brief introduction about network layer. As we mentioned, we discussed about virtual circuit, which involves a path establishment from source to destination and will make a reservation of resources of all the devices which are involved in the path from source to destination. Let us try to discuss the second type of network called as datagram networks. The networks in which the network layer tries to provide connectionless service, we refer it as datagram networks. In our previous class, we tried to discuss about the first type of networks called as virtual circuit networks, in which the network layer provides a connection oriented service where a path has to be established from source to destination. So in our datagram network, there will be no call setup required at the network layer. And similarly, there is no requirement that all the routers which are in the path from source to destination should know about end-to-end connections. So no network level concept of connection required. So in previous virtual circuits, a connection setup is required where every individual router which is a part of that particular routing path has to know the entire route. But in this scenario, we doesn't require those connection requirements. So every router which is a part of the network which are involved in the routing path will receive the power packet, will verify the destination address, and according to that particular destination address, it will select one of its output port and try to forward the packet or datagram. So here the forwarding of the packets will be done based on destination host address, whereas in case of virtual circuits it is happening using virtual circuit identifier. Let us try to take a simple example to understand our datagram networks. Here we have the source which is generating the data. Data is transmitted from application layer to transport layer. The transport layer data is converted in form of segments which are forwarded to network layer. So network layer which receives a segment from the transport layer will convert it into datagrams. So here our the sender will be trying to send the datagrams. So we have few datagrams which are sent by the sender, and this datagrams, to reach to the destination which is indicated here, it has to travel through certain set of routers. Okay, now how do we try to forward this datagrams from source to destination? So the datagrams which are to be sent will be received by the routers which are in the path from source to destination, and whenever a router receives a particular datagram, it verifies the destination host address or destination IP address. Then it has a forwarding table based on the destination IP address, and according to that it will try to forward the datagram to a particular output port which is trying to connect to the devices which are in the path to the destination. So this is how you could find a difference in the approach from virtual circuit, where you are using a virtual circuit identifier. In that case, here we have a destination host address. There a path has to be established before the data transfers. Here there is no requirement of any path or connection to be established. So connection setup which is required in virtual circuits is not required in case of datagrams. And one more important thing that need to be understood is in your datagram networks, so different datagrams of a same sender to the same destination can follow different routes. So there is a chance that the datagrams which are transmitted by the sender will be received at the receiver in an order different from the way it is generated. For instance, I generated 1, 2, 3, 4. Because of the traffic or some route it has followed, there is a probability that the datagrams will be received in a different order. Like instead of 1, 2, 3, 4, we may receive 1, 3, 2, 4 or 4, 3, 2, 1. Okay, so that need to be understood. Right. When a sender tries to send the data to from the source to destination through a series of routers. So this is the packet or the datagram which is tried to be sent by the sender. So in this particular datagram, you find this particular portion which is actually referring the IP destination address in the packet's header. So in the packet which we are receiving, in the header part, we have this IP address. So this is reached to the first router. Now in datagram networks, every router has a local forwarding table. And what are the contents the local forward table have is, we have one column called destination address and the other column called output link. And to prepare this local forwarding table, so the routers will be using an algorithm called routing algorithms. Now here, what do we mean by term called address range? To understand this particular terminology, let us take a simple example of our node this seating arrangement during the exams. So you don't find every hall ticket number mentioned at the main wall. So what they try to do, there are around 500 students. So they will not put every roll number and show the arrangement. So what they just to do is 1 to 24, room number 1, 25 to 20, 48, room number 2. So what it happens is, when you look at your roll number, it's 40. So where it is between 24 to 48. So you can understand that you belong to room number 2. For instance, third room number range is 49 to 72 and your number is 56. So though it is not directly mentioned, but you will understand that 56 belongs to room number 3. Similarly, what happens is, here we have 4 billion IP addresses, and to mention each IP address in the routing forwarding table, it becomes a very complex task. So what we try to do is, we try to give the certain address ranges. For instance, here I have 4 billion IP addresses. So what I do, I divide into 4 parts. 0 to first 1 billion, I will use an output link 3. So 1 billion to 2 billions, I will be using output link 2. 2 billions to 3 billions, 3, that kind. So here I will have different address ranges which will mention the which output link. For instance, here the router is made up of 3 output links. So first address range, it will be using an output link 3. For next, second and third address ranges, it is going to use the output link 2, and for the address range 4, it will be using output link 1. So in this way, whenever a datagram is received by a router, it looks at the datagram's header so that it can find the IP address and find out from the IP address, using the forwarding table, it will identify from which output link that particular datagram has to be forwarded. This is called datagram forwarding table. In the previous slides, we were talking about a datagram forwarding table consisting of two columns. One is destination address range, which actually consists of the address range, and the second column consisting of the link interface, means the link through which that particular datagram has to be forwarded. Now look at this particular table. I have 4 rows and 2 columns. Let me understand that all the datagrams which I am going to receive have some common element. What is that? First of all, remember, an IP address is an universal address used by networks for host to host delivery, which is of length 32 bits in IPv4 version and 128 bits in IPv6. Currently we are talking about IPv4, so we have 32 bits. Now here in 32 bits, the first 8 plus 8 plus 4, 20 bits are common. So the variable bits are the last 12 bits. So what is the range? 0 0 0 0 to 0 0 0 0 0 0 0 0 0 0 0. So all the last 12 bits are zeros. And what is the maximum value possible with all last 12 bits? So the first 20 bits are common and last 12 bits can be ones. This is the maximum range. So what I'm doing is, so this total addresses, I'm going to divide into 3 address ranges. What is that? The first 20 bits are common, 1100 1000 0001 0111 0001 is common, and from starting 000 all 12 zeros, first I am dividing up to 0 1 1 1 and followed by 8 ones. Okay, so the first of this 12 variable bits is still 0. Next range starts from this bit is 1 and remaining all 11 bits are zeros up to 1000. So last 8 bits are ones. This is my address range 2. And for first address range I am using a link interface 0. For second address range I am using link interface 1. The next third address range, first 20 bits are common. Then we ended with 100 all ones. Now we move for 11 and 1001. Then from here all zeros we will be having 1111. So all this remaining address will be assigned with link interface 2. Suppose my address does not belong to any of these three address ranges. So what I need to do? Then if the address which I have received in the datagram is different from all the above address ranges, I will opt for fourth destination address range, which is otherwise, and I will select the link interface 3. So this is how the datagram forwarding table will be used in datagram networks to forward a datagram which is received at the router. Right. So far we were trying to understand what is a forwarding table and how the router uses the forwarding table to find out the suitable interface. Now let us look at a concept where the router has received a particular datagram and it has to be forwarded. Now how do I exactly determine the link interface from which I have to forward this particular datagram? For this I am using a concept called longest prefix matching. What do we mean by longest prefix matching? Once when I have received a 32-bit IP address, okay, so when looking for a forwarding table entry for a given 32-bit IP address, I'm going to use longest address prefix match. That will be matching the destination address. So what do you mean by this? So out of 32 bits, so which particular address range, the maximum bits match with the address range. For instance, I have just taken you a simple forwarding datagram forwarding table with the destination address ranges as below. Look at this. The common portion for all those columns we actually refer with network ID, and the variable will be called as host IDs. The first destination range, the first 20 bits as we discussed earlier is common. Now next starts with 0 and it can be 0000 and it can be up to 011111. Okay. Now next we have just discussed the next starts with 1000 and remaining is 00000000 up to 11111111. Next we have 1001 and the remaining address ranges. Right now in this I have received a datagram with an address, so 110010011010110101101001. I need to apply longest prefix matching. However, the first 20 bits are common because this is a network ID indicating they belongs to following network. So this is common. Now next fifth element, which fifth bit of this third field is 0, and here you find fifth bit 0, 1101010001. Now here what is the range we have? From 0 0 0, all zeros, we have the range up to 0 0 0 0 0 7 and 8, and we have this up to the range 1 1 1 1 1. So this is zeros and we have all this bits as ones. Now if you look at the address, the destination address which we have received from the datagram, so 0110
10100001, this particular, among all this, it doesn't match the remaining. Why? Because the fifth bit is 0 here, but remaining the two cases, the fifth bit is 1, so it is not matching. So among the three cases, so not only 20 bits, the 21st bit is also common for link interface 0 and the destination address. And you can find this particular part 110.101.0.0.0.1 can be a part of this particular case, which is 110 can be a part, one number among this range which we have. So out of this 4, which is the interface from which the following datagram will be forwarded? The interface 0. So we are trying to find out the longest address range where which matches with the required datagram's destination address. That particular process we are referring it as longest prefix matching. So this is how you are trying to forward a datagram which is received at the router by trying to implement longest prefix matching and then finding out a suitable link interface. Well, categorizing the networks based on the type of service provided by network layer, we categorize the networks as virtual circuits and datagram networks. Let us look at the origins of these two circuits and how they are different from each other. The first type, called as virtual circuit, one of the best examples is asynchronous transfer mode. So the reference or the origin of this ATM or virtual circuit is it has evolved from telephony. Remember your conversations on landline phones? Before you start conversating with your other party, first through they need to establish a path from your telephone to your destination or the targeted person's phone. Then when he picks the phone and the call is established, then you start exchanging the voice. So similarly here also, before the data transfers, a path has to be established between the source and the sender, and this concept we call it as virtual circuit. Here similar to human conversation, strict timing, reliability requirements, and need for a guaranteed service. So when you are expecting a guaranteed service with in a reliable delivery and order delivery, all that are our requirements, then circuit which we have to adapt is definitely the virtual circuit. Okay, as we said, that it's a dumb end systems which require a long processing, and even after completion of the conversation or the exchange of data, the call has to be terminated because there is more handshaking required for starting the conversation or the exchange of data and for ending the conversation or exchange of data. So definitely the complexity involved in the virtual circuit is higher compared with the datagram. Anytime any transfer of data cannot happen unless a path is established. So definitely you find more resources requirement and more process involved. So this is comparatively complex. Now coming to the other one, which is called internet, is an example, and the approach, the network is called a datagram network. The data, what is a datagram network? I got some data, I convert it into datagrams, and I transmit through the network. Now my datagram may travel through different paths. So there is no one particular path that all the packets has to transmit. Some data transmits through path 1, the other travel through path 2, and finally at the destination they may come out of order. Very few may be lost. It's not guaranteed. It's only a kind of service. But what is the advantage you get when you adapt for this internet or datagram kind of network is the complexity procedure which is involved in virtual circuits is not required here. No connection setup is required. No reservation of resources is required. So we can have many line types. So path 1 is involving one characteristics, the other one will be involving the other characteristics. And all this guaranteed and the resources required, that much will not be required in case of internet or datagram. But problem is we don't have reliability guarantee. At the same time, the order of delivery might be different, and there is a possibility of getting the data more corrupted. But still, it's a simple process and doesn't require much complexity. When something like a higher layers like transport layer or data link layer takes care, the lower layer like data link layer takes care of this flow and error controls, where we can go for a connectionless service network like a datagram network. But remember, whenever you are using a datagram network, for reliability, for flow control and error control, you have to use a higher end or a better protocol like TCP. But in case of virtual circuits, at the transport layer we can go for UDP, because this takes care of all those important functions. This is a brief comparison between the virtual circuits and datagram networks, and please keep in mind this is one of the very important question, where virtual circuits is suitable for connection oriented networks like asynchronous transfer mode, and datagram networks will be suitable for best effort service like internet. So far we discussed about the two types of networks based on the service provided by network layer, which is namely virtual circuits and datagram networks. One of the important element which plays a key role in both the types of networks is router. So now let us try to understand the architecture and overview of router and what are the important elements of this router. So two major functions which are performed by the router in the network is, first, whenever a datagram is reached a router, it receives from the input port, and using the forward table it has to send it to the appropriate output port or link interface. This particular function delivered by router, we are referring it as forwarding functions, forwarding the datagrams from incoming to outgoing link. Now, one more very important role to be played by routers is, from the source to destination, to implement the host to host delivery, a path has to be established, for which we need to have different set of routers along with the source and destination. Now, what are the routers to be involved, and what is the path to be followed by the datagram from source to destination will be determined by routing algorithms. So one more key function of routers are to run the routing algorithms, so that we'll try to identify the optimum path for which the routers are using a particular set of protocols. We have different types of routing protocols, namely routing information protocol, open shortest path first, or border gateway protocols. So two major functions, forwarding and routing functions, and to implement these functions effectively, a generic router architecture is shown below, which has four important components. So the router, to deliver those two important functions, will be using four important components. So what are those four components? First one, to receive a datagram from the sender, the router uses its first component called router input ports. Once the datagram is received by it, here router input ports have three elements which we'll be discussing in the next slide. But once the datagram is received, then it will be forwarded to the high-speed switching fabric. Now there is a small comparison between terminologies called router and switch, but just understand, switch we have two types. The first type of switch which operates at network layer, we can refer it as a router, but there is another type of switch which operates at data link layer, and that can be referred with a second layer switch. Okay, sometimes we also refer with names like bridge also. Okay, right. Now the switching fabric is the element which will try to determine the appropriate output port link interface, and means the forwarding table will be calculated by this switching fabric, and the routing algorithm which is required for routing the packet from the source to destination will be performed by an element called routing processor. And based on the route that has been selected based on the algorithm, what happens is the appropriate output port out of the n ports which are available has to be identified, and that datagram will be forwarded from the switching fabric to the concerned output port, from which that will be forwarded to the next router, or sometimes if it is the destination, so from this it will be connected to the destination. So four important components are required for a router to implement the forwarding and routing functions. What are that? Router input ports, then high-speed switching fabric, we have a routing processor, and then router output ports. The functions which are performed will be forwarding. So for we refer forwarding data plane, which is majorly concerned with the hardware components. The other one is routing processor to determine the routing algorithms and the routing path. So that will be concerned with the routing and management control plane, which will be dealt with the software, right? So make sure you people remember this because it's one of the important questions. Now so far we just try to understand what are those different components involved in a router for implementing its function. Now we'll try to have a deeper understanding of each of the component of the router. Now let us look at the first important component of router called input port, and what are the functions performed by the different elements of input port. So as we mentioned, the input port consists of three blocks, namely line termination block, link layer protocol, and lookup forwarding and queuing block. Okay, the first one is line termination. So this is the one which is actually responsible for receiving the datagram sent by the sender or the previous router. So this particular line termination is the one trying to connect you to the router, and it performs the physical layer function of terminating an incoming datagram for physical link at the router. Okay, so the second block of your input port is link layer protocol. So what is this particular link layer protocol role is? This particular block of input port also performs the link layer functions needed to interoperate with the link layer at the other side of incoming link. So what is the other side of incoming link? So with that, it has to be interoperable. So for instance, so like I am sender and this is the router. So the interoperable we need to maintain, and that will be performed by the link layer protocol. And third one, this is the one which is actually trying to connect you to the switching fabric, which will try to forward the datagram to appropriate output port. So what we have in the third block of our input port is, first, it will be once a in case of datagram network, a datagram destination is identified. Look up at the output port using forward table in input port memory. So we are going to have different types of forwarding techniques using in the switch fabric. So we have three types which we'll discuss in short. So for that, either for datagram destination IP address, or if it is using a virtual circuit identifier, so that will be identified so that it can be forwarded to the switching fabric. Suppose the rate at which the datagrams are received by this particular router, we actually refer this the terminology called line speed. Now this speed means it is receiving 5 packets, but switching fabric can process only one datagram at a time. So what happens is, when first one is in process, remaining 4 will be received but kept in the queue. So this is how it is trying to indicate. So your this particular third block, which we are referring it as decentralized switching, is trying to maintain a queue with this receiving of the datagrams is at a greater speed than the capacity of the switching fabric. So three important parts of input port. First one is line termination, through which we are actually receiving the datagram to the router. It performs the physical layer functions, and link layer protocol functions will be delivered by the second block, so that we have interoperability with the other side of the link. And the third block, decentralized switching performance, and what it exactly does is, it will be trying to identify the destination IP address or the virtual circuit identifier, and it will be trying to measure the line speed, and in case of it is greater than the switching fabric speed, it will try to implement a queuing mechanism. The next important component of our router is switching fabrics. So the input port, the third block, that is decentralized switching, will forward the datagrams to the switching fabrics. And what is the role of switching fabric? It transfers the packet which it received from the input buffer to appropriate output buffer, right? the rate at which the packets can be transferred from inputs to outputs by a switching fabric. We call it as the switching rate of this switching fabric. It's often measured as a multiple of input or output line rate. For instance, if I got an input line rate as R, then I will try to measure this switching fabric switching rate as n times R, right? For an n inputs, the switching rate, suppose I got n number of inputs, the switching rate will be n times the line rate. One line rate is R. I got n inputs, so my switching rate will be n into R, where n is total number of lines and R is the line rate of each input. Okay, basically we have three types of switching fabrics implemented. The first type of switching fabric is called memory based. The second type of switching fabric is called bus based, and the third type of switching fabric is crossbar. Let us try to understand all these three types of switching fabrics. The first one is called switching via memory. So what do we mean by switching via memory? So this is actually the first generation routers, and these are similar to traditional computers with switching under direct control of CPU. For instance, you could look at this figure. Here you have input ports which are actually receiving those datagrams, and this datagrams which are received by the input port will be forwarded to the CPU. So this is something like a memory unit of part of CPU. Okay, now traditional computers with switching under the direct control of CPU, and here we have a part of CPU called memory. The packets which we are received are copied into the memory. Then the CPU tries to extract the destination address from the packet's header. The memory is storing the packet, and CPU is trying to extract the destination address from the packet's header. Look up output port in the forwarding table. Now here we have a forwarding table in which we'll try to find out for that particular destination address what will be the suitable output port, and copies that particular datagram to the output port. So what is the thing that we need to remember for switching via memory is the speed limited by memory bandwidth is only 2 bus crossings per datagram. So next we'll talk about what we mean by crossings there. Here when you are using a memory, we have certain limitation in the performance, and in any instant of time the CPU and the memory will be able to access only one packet at a time. So comparatively with the first generation, it is delivering the tube, but the performance is not up to the mark. So definitely we'll go for an enhanced version of switching fabric. The second type of switching fabric we are referring is called as switching via a bus. So look at this figure. Here you have the input ports, here you have the output ports, and this input ports and output ports are connected by a bus which is acting as a switching fabric. So a datagram from an input port memory to the output port memory is shared via a shared bus. So this is shared among multiple input ports and output ports. So the bus we are using is a shared bus. And what is the bus contention? It's how it is being utilized. The switching speed of this is limited by the bus bandwidth. So the capability of how many packets can be forwarded and how many devices can be connected, everything will depend on the bus which we are using here and its bandwidth capability. And here also the processing speed is one packet at a time, and the bus which we are generally used is a 32 Gbps bus. So Cisco 5600 model. This sufficient speed for access and enterprise routers. So switching via bus, they are using as a bus as a switching fabric, whereas in the previous case a memory which a part of CPU will be used as a switching fabric. The third type of switching fabric we are using is called as switching via an interconnection network. To implement this, what we are trying to do is we are using a certain series of crossbar switches or Banyan networks. So it forwards multiple packets in parallel. For instance, A has some data to be sent to Y here, B got some data to be sent to Z, C has some data to X. So here all the three input ports can actually transmit the data to the respective output ports. So So we can have multiple packets that can happen in parallel. For implementing or to build this particular switching via interconnection network, we are using Banyan networks, crossbar, or other interconnection nets. And these are initially developed to connect the processors in multiple processors. So for instance, the example we would like to take is we would like to connect an input port A to forward a packet to output port Y. Here XYZ are output ports and ABC are input ports. And now what happens is here we have different connections. We'll try to use a different pen. So here these are the switches. Generally what happens is when no connections required, the switches are open, but here A and Y initially they are open, and whenever a connection is required, what happens is the switch of A and switch of Y gets closed, and now a path is established from A to Y, and then the datagram will be transmitting from the input port A to output port Y. So once the datagram is completed, transfer is completed, the switch will be released and again it will be in open state. Now the switching via interconnection network is an advanced design because it is performing much better compared with the other two models. It will be helping in fragmenting the datagram into fixed length cells, switch cells through the fabric. For instance, I got a very big data to be transmitted. So what I try to do is I will divide the bigger data into smaller units called datagrams, 1, 2, 3, and three different datagrams will enter three different input ports and try to reach to the three output ports parallelly, and I could save a lot of time and later again they can be combined. So here we are trying to reduce the delay in the transmission. So these are the three different ways in which you can actually implement the switching fabric. Switching via memory, second one is switching via bus, and third one is switching via interconnection network made up of elements like Banyan networks or crossbar switches. The third important component of your routers is referred as output ports. Now earlier input ports are trying to connect to the switching fabric. Here from the switching fabric we are connected to the output ports. So the components which we have as a part of output ports are almost similar to the components which we have as input ports. Now first we got an datagram buffering and queuing mechanism, which is the third block. Here it will be the first block because this is where we are trying to connect to the switching fabric. Suppose here what is happening is when the datagrams arrive from the fabric are faster than the transmission rate. I have a one transmission at rate, but I am getting from fabric 4 to 5 packets, so I cannot transmit them all at a time. So what I do is I'll try to keep the remaining ones in the buffer and I'll transmit one packet at a time, and once it is done the next will be transmitted. So here we will have a datagram buffer which will be helpful for queuing if the line transmission rate is lesser than the switch fabric switching rate. Okay, the second one is link layer protocol. The functionality is similar to what we have heard in the input ports, so it will be trying to bring a compatibility with the link that is used at the other end. And the third one, the line termination. The line termination at the input port is trying you to connect to the sender or the router from which you are receiving the datagram. Now once an appropriate output port is determined, from that port we have forward either to the destination or to the next router in that particular path. So this is the three important elements of output part. Buffering is required whenever your line speed is less than the switching fabric switching rate, and make sure scheduling discipline chooses among queued datagrams for transmission. The last component which we have of a router is called routing processor. So the routing processor, so far the first three elements, that is input port, switching fabric and output port, is responsible for forwarding function. But one more very important function to be delivered by the router is routing function. So that particular function will be taken care by a component called routing processor. The routing processor executes the routing protocols, maintains the routing tables, and attach the link state information and computes the forwarding table for the router. It also performs network management functions. So the key important functions of the router will be performed by this particular component called routing processor. Using routing algorithms, now try to find out the routing path. At the same time, it will also try to build the forwarding table so that it can be used for the remaining components. Okay, so let us try to uh, stop our class here, and before I wind up the class, let me give a quick recollection of things that we tried to discuss in today's class. The first thing we tried to discuss today was the second type of networks based on the service provided by network layer called datagram networks, which is a connectionless service. The datagrams will be traveling in different paths and will be out of order, but here for transfer of data we doesn't need any kind of circuit setup or connection setup, and the resources required for the transmission in datagram is less. Because of this, the complexity involved in the datagram transfer is less. Datagram does not provide any kind of guarantee, but this will be suitable when the other layers of OSM model like transport layer will be taking care of flow control and error control and securities. Then we try to put a comparison between the origins of these two networks called virtual circuit and datagram network. The last thing that we try to discuss is a very important topic called the architecture of routing router, which is used for the two important functions called routing and forwarding. So the four important components are part of a router. The first one is input port through which it will actually receive the datagrams. We have the three elements there: physical layer, link layer protocol, and decentralized switching. Then we have switching fabric, which is again categorized into three types. It will be trying to determine the forwarding table to link the appropriate output port for the given input ports. And the three mechanisms are switching by memory, switching by bus, and switching by interconnection network. The third component of router is output port. This is the one through which the datagrams will be forwarded to the next devices. And there also we have three components. The first one is for queuing, and this is required when the line speed is smaller than the switching fabric speed. Then we have the data link layer form, and the last one is our physical layer, which is actually trying to connect to us the next element of the network. And the fourth important component of our router is routing processor, and this is the most important component which will actually execute the routing protocols. It maintains the routing tables and also generates the forwarding tables, and it also takes care of network management functions. So now next class we'll try to discuss about the queuing mechanisms which is used in our routers, and then we'll try to discuss the remaining concepts of network layer. Meet you in the next class. Thank you.